So, welcome everyone. Welcome to this talk of today's talk of this series. We are pleased to have Professor Stephen Rudek with us today. He is an assistant professor at the University of Wisconsin Madison, US. He was an assistant professor at the Technion, which he joined after his postdoctoral training in Mary Boyce's lab, MIT. After that, he is now working in the University of Wisconsin Madison. Stephen gained his PhD from Ben Gurion University, Israel. He was a visiting graduate student at Caltech and Harvard universities, and he has received his MS and BS degree from St. Petersburg University, Polytechnical University, Russia. Okay. His research mainly focuses on mechanics and physics of soft microstructural materials, including soft active materials, bio-inspired materials, switchable functional composites, and biological tissues. He uses a combination of analytical and computational approaches, as well as 3D printing and experiments to understand nonlinear behavior of these materials. So today he will be talking about instability-driven pattern formations in soft heterogeneous materials for dynamically tunable functionalities. So over to you, Professor Stephen. I will disappear now, and then I will be appearing at the end again.
Thank you, Anshul, for the very nice introduction and for inviting me to this series. I'm very glad to do so, and especially in these times. So again, thanking the organizers. That's really an honor for me to deliver this lecture within the IIT Mechanics of Materials webinar series. I never visited the IIT system of universities, but I have interacted with many excellent researchers from these institutes, and I also enjoyed working with the students and the postdocs from IIT system. So I'm currently one PhD student from IIT. Nitish Arora is working with me, and I back at the time of working in another IIT, that was Israel Institute of Technology, Technion. I had the pleasure to work with another IIT Madras alumni, Turkish Dora, who was a postdoc with me, and he also continued to working in Institute of Technology system. Now he's in Karlsruhe Institute of Technology. All right, so that's hope that soon we'll have a chance to travel, and so I can visit physically many of IIT institutes that I very much look forward to. Now been to India, that will be that is on my plan. So, but for today it's virtually. So that's let's try to make it work. Right, so. I will be talking about these instability-induced patterns that we can obtain in soft materials. So very important word here, soft. Just the material will be deforming a lot. There will be nonlinearities that will come from that. And I added the last line here in the title to try to connect this phenomena to some potential applications, but we'll discuss whether it's possible to extend it there or not. And basically, the talk is divided into two parts. So the first part will be, I will just review some of the patterns that we can obtain by using this elastic instability phenomena. And then we'll dig a little bit more into the ways how these patterns can be used to manipulate elastic waves. So you see here this second type is called acoustic metamaterials, but here I typically in a way of a disclosure saying, okay, so I call it acoustic metamaterials here mostly for the fancy name, and but more properly, and also it fits very nicely the block here. But the more appropriate title of this section would be elastic waves in soft materials. But acoustic metamaterials also could work, I hope. All right, so let's start from the first part, and this is our review of things that we're going to talk about, instabilities. So basically, we'll start from the talking from relatively simple and basic example of the formation on wavy or wrinkling patterns in soft materials, in laminates. Then we'll also extend that into a little bit into 3D system of fiber composites and see what we can obtain there. Then back again into 2D, and that's where some sort of the connection to these metamaterial systems of materials with negative Poisson ratio behavior and some additional interesting pattern formation that we can exert based on our knowledge in instabilities in a relatively simple system. And then finally, there's something relatively new that we worked with the Turkish doors that already mentioned, that are some new phenomena that we discovered in experiments and trying to explain it from theoretical point of view. All right, let's start just without wasting much time. So starting from simple laminate, this picture actually from an experiment. So what you see here, the grayish area is soft matrix, and we have a stiffer layer here, and so and here this is the ratio between the thicknesses of the stiff layer and soft matrix, and this is the ratio between the initial shear model, Young model, if you like this. And so what I'm going to do is I'm going to compress that in the direction of laminate. And of course, you expect that similar to Euler buckling, so this at certain critical strain or critical force or stress that we apply, this stiffer layer will buckle. And the way how they buckle will be regulated by the stiffness of the surrounded matrix. So it's close to elastic system. So when we release the load, the material goes back to the initial state. So this to just emphasize the reversibility of this. Now, I'm quickly going to change this the geometrical distribution of this. So now we put these layers closer to each other, so effectively increasing the volume fraction of the stiff layers. And so the ratios here are D to T is 6. And I keep the same materials in this 3D printed laminate. And then when we compress it, so then we already can observe a change in the patterns that we obtained here in the wavelengths. Now, and finally, to show you that the tunability by the material constant, the contrast. So now we take two printed with two different materials. There's quite significant difference in the initial material constant to more than 1,000, and then we can travel up to long wave type of instability. So we'll discuss the difference between these from theoretical point of view and how they can be analyzed. So, right, so before we go there, just a very quick illustration of this experimental picture. So we'll see this a little bit in the right, almost certain dynamics, but of course it's quasi-static, it's very slow. So we try to kill the viscoelasticity behavior for this. And we'll explain that why very soon. So again, so this is the formation of this wave pattern that can be very accurately actually predicted by the theoretical analysis and by numerical simulations. Now, I will have only one slide on the background of the theory of that, so but that could be another long lecture, maybe even more on the type of analysis of the instability in the nonlinear elasticity. So the analysis basically is set on what is called small on large concept. So when we deform the material to large deformation, and then on top of that we perform some incremental linearized analysis of the stability. So superimposed small disturbances to see if they grow fast after that. And typically, to detect these type of instabilities in this superimposed incremental analysis, so what we use is called so-called block or block wave analysis or block Loci analysis, when you essentially then can scan for different wavelengths and can detect different instability developing at different wavelengths. So there is, however, a very important case when K, this wave number that we scan when we try to detect instability, that K is going to the limit to a very small number, and that essentially corresponds to the situation when we can use loss of ellipticity analysis, which is actually can be performed in many cases analytically. So then the only thing that we need to perform that is to obtain the information about the effective behavior of the material in terms of the tensor of elastic moduli. And so, we just need to satisfy this particular condition for any combination of these vectors n and m, and so there are some constraints that will be applied on these vectors. For example, for incompressible materials when n and m need to be orthogonal. But okay, so this very short two blocks. Behind that is a very solid and rigorous theory, which I omit here for the sake of time. And then we perform this analysis in some cases analytically, in some cases it can be implemented also in finite elements. But in this way or in others, so then we obtain the information of what happens at the buckling and what to expect the material to develop after buckling. And that's where we go into the post-buckling analysis to help finite elements to find these patterns. So again, this is just illustration for this similar laminate system, and that's when we can numerically visualize the distribution of deformations. Here's the only one component of that to illustrate. And what you expect here when this material buckles, again, so this is quite typical behavior, but this is given here on the example of relatively simple, this soft laminate material. So what you typically expect to see is that in stress-strain behavior, so your laminate will have, if it remains flat, so that will be this straight line, but when you approach the buckling point, then you obtain softening, if you like, let's call it in this way, so you have a softer behavior of the material, and when it goes into more energetically favorable mode. And then also can that correlates with the increase of the amplitude of these imperfections in terms of the wavy shape here, when we can monitor that in numerics, of course. And so that's the point where these imperfections start to grow very fast and that manifest the instability here. Now, for a simple system, and I already mentioned some inelastic behavior, but if we assume that this is material is purely elastic, then we have only two parameters, basically the geometry, let's say thickness ratio, volume fraction, how much of stiff or soft material we used in our system here, and the contrast in the initial stiffness of these materials. And so these two parameters uniquely define the configuration that we can exert when we apply deformation and develop instabilities. So one of the motivation for this research is to provide access to as many microstructures and the different behaviors of these for initially identical or the same material, and the way to extend that. So basically, once you, for example, printed particular structure, so you are limited to only one configuration. And but since the material is inherently, so soft materials inelastic, so we can use this inelasticity to actually try to travel within this map. And so that's what we try to illustrate here, the use of rate-dependent behavior of soft material that we can try to tune this wavy structure upon instability. And so here's an example of to illustrate that. So that's so first let me explain it here. So this is a measure of strain rate. So what you will see on the right side is the relatively slow loading, and here is relatively fast again, not extremely fast, but relatively fast loading. And so I take identical the same composites, same laminates, and load them to exactly the same level of deformation. And you can see that for this, that we loaded much faster than, so we were already exerting the viscoelasticity in the layers, while the viscoelasticity of the matrix is rather weak, again, compared to the layered material. So we can already obtain the developed instability here, while the same level of deformation with the same identical material still stable and the layers are still flat. So we also can model, of course, this in finite elements, also that viscoelasticity is quite a tricky subject, and there are many constants that may not be easy to capture very accurately, but this way or another we can also obtain the information in numerically in what happens locally in terms of stresses and how they relax, etc. So we can also continue further to show that, of course, the other guy will the same sample that we load slowly still will buckle. Just we need the larger strains for that, and for the faster loaded one, so we already have a very well developed pattern that also can be predicted with numerical analysis as well. Right, so this I'm shifting from 2D system to 3D, but we're still thinking about rather similar system. Actually, laminates historically many times we used to make some predictions on 3D fiber composites, and that doesn't make sense as you think about the cross section of this transversely isotropic fiber composite. So the cross section will look quite similar to the 2D laminate or 3D laminate. And now it appears that if we obtain the nonlinear effective behavior of this material, the energy functions and the stress-strain relations, then we can use the machinery of that loss of ellipticity analysis that I mentioned for the macroscopic instability, and then we can derive a compact formula based on this effective energy function that were derived from the micromechanics based approach. And we can obtain the value for the critical stretch, so we can answer the question when the material will buckle. And so this critical stretch that is given by this compact formula, in which all the components are defined in terms of the actual micromechanical parameters. Basically, we have the information here about the volume fraction of matrix and fibers and the properties of initial moduli of fiber or matrix. So this formula can be derived for the weakly nonlinear materials, so when we have non-Neokian matrix and fiber, but also can the similar formula can be derived for materials with a stronger nonlinear behavior, such as GENT materials. And so to illustrate that in the comparison, so this is the critical stretch that we derived versus the fiber volume fraction. And so this is the analytical prediction for laminates in 2D. Again, so this is for long wave, and that's why I put here this illustration to indicate that basically what you see is that so the critical stretch 1, meaning that material is undeformed, and then when you increase the compressive deformation along the layers, so then at a certain point, depending on the volume fraction in the material composition, you will meet this curve, and that's where the material is predicted to become unstable, and all the region here under this curve is unstable. So this is for 2D laminate that we're going to compare this to the result for 3D fiber composite, so that would be a more fair comparison to allow these laminates to deform in 3D, and that's how these behaviors look like. Now, I'll not discuss that much and just jump directly to what happens at the small volume fraction. So this analysis, the loss of ellipticity analysis, predict that composites to be extremely stable when you have lots of matrix and only a little bit of your fibers. And this is, of course, not very realistic. And that's where the microscopic instability analysis that accounts for the wavelengths and becomes very important. And that's where you actually, if you do that, then you detect that instability at the smaller length scale in this configuration develops much earlier. So you don't need to compress, apply a very large deformation to exert that. And so this again is for laminates and for fiber composites. So there are some differences in the behavior, and one of them is hopefully that that some numerical predictions indicate appearance of 3D structures like that. All right, so this is again basically to answer the question when the instability happens, or what is the critical stretch, and hence we can determine what is the critical stress that is needed to be applied to trigger development of these patterns. And now the next question is what actually happens, and for that we have this critical wave number or critical wavelength, so just more convenient to plot it as a wave number. Again, this is how it looks for the laminates, either in 2D or allowed to deform in 3D. And so very similar behavior in that, and of course that's expected as basically the same material, just a little allowing to deform it in one more direction instead of constraining plane strain. Now I'm going to compare this to the fiber composite, and here it appears that although the trends are very similar, but the difference in the wavelengths, so the characteristic wavelengths at which the instability develops, is quite large. So here, for example, can compare it for smaller volume fractions, so the factor maybe 2 versus 16, so more than 8 in this case. And just again to illustrate, right? So when I decrease the volume fraction, so as you can see, when you increase the wave number, or effectively, because it's an inverse of that, so we decrease the wavelength, and here the evaluation of this just to illustrate. And in some cases, numerics also shows some interesting eigenmodes that showing these helical patterns, which appears to be not that easy to actually obtain with instability. So it will be very interesting to look to the causes and reasons why that would or would not develop. Now, so with that in mind, we did some experiments on these 3D printed fiber composites, and this is again that's what you expect from the materials, this type of behavior, so stress strain behavior. So material lose stability in buckles somewhere around this peak, and then after that you have a much softer behavior, and that is consistent for different volume fractions. So just showing you this experimental result with this stress strain behavior. Then it becomes a little bit tricky to detect exactly where this buckling happens, or more prominent, probably easy here for the larger volume fraction when they have more prominent stiffening. So, but maybe not that straightforward to detect where exactly the buckling happens. So there's some speculations about which point you can choose to say that the buckling already happened. And so, but in this way, now that we can collect these points and then put this as a plot all together as printing this critical strain versus fiber volume fraction together with this simulation. So this is a simulated trend, and so again, and this is for a limited case when we have a single fiber. So we hope that simulation, of course, converged when we have a very small volume fraction to that level, so that gives us some level of confidence in simulations. And then when you put the experimental here, so that follows its trend very nicely, and also captures the transition that indicated that this voided circles and symbols that are filled from this macroscopic and what we call microscopic instability. And just we'll look into that with more illustration on the next slide. So the transition is happening here. So again, predicting numerically like that. So the region of small critical wave numbers corresponding to very large wavelengths versus the transition to the finite wave numbers and finite wavelengths here as we cross this threshold volume fraction. And so again, the single fiber, just to indicate that we are, at least here we are very good. And so now putting the experiments on top of that, and so that seemed to work very nicely in terms of capturing this transition from long wave type of instrument. This looks like laminates, but you will have to believe me that these are actually fibers, and so there is, and that's partially the explains the quality of these figures, because we're taking the pictures through the soft matrix, so the fibers are this is not the laminates that go through the whole thickness. And you can see that there is this transition happening from long wave into microscopic type of instability. So also it doesn't really, so qualitatively, so if we compare a number, so there will be quite significant difference, but fundamentally, so the transition is captured, and that makes me quite happy with this agreement of the experiments and theoretical predictions. And so then we looked into more details into how we can use different arrangements as we, for example, print these composites to actually control how these fibers collectively behave and how and where they will go in buckle. And so here the control parameter in the initial microstructure is this aspect ratio of basically how close we put these fibers in one direction relatively to the other direction. And again, so these are the predictions of the critical wave number. So we can see that there is a quite significant tunability, also for the quite large span of aspect ratios, but the factor here is 5. And so basically for you, again, so you can tune the wavelengths of all these buckling patterns by a factor of 5. And so it's interesting that there is actually certain configurations for which fibers will buckle into different direction that one would expect. At least I expected at certain points. So I expected the fibers always to go and buckle in the soft direction. However, for certain configuration, they prefer to do a very strange mode of buckling when they cooperatively buckle in this direction, which is something that works counterintuitive. But this is very strongly also supported by what we see in the numerics and also in the experiments. So this is so we actually checked that and saw this behavior too. And you can see that experiments also, again, not matching perfectly this curve, but the trend is captured in experiments very nicely. So now one I will mention, not going into much details, is also the consideration of this distribution, different distribution of the fibers in the cross section. Some interesting result that we obtained. So it appears that the condition at which it happens, the instability develops, is bounded by two cases. So the first one is, of course, trivial. Basically, is we limit that by this symmetric square arrangement. So that will be our lower bound here. But then the upper bound will be actually predicted very accurately by completely different system of laminate. Also, it does make sense, because if you think about of putting all the fibers very close to each other, so then effectively they are forming a stiffer layer when other fibers are very far from them. So we have a column that you can approximate by the behavior of a laminate of a whole layer that is stiffer, but they reinforced with these particles or fibers. Like, so this is providing the upper bound. So we cannot go beyond that. That's an interesting result that we observed. Now, so that now we're going back from 3D to 2D to something more exotic, let's say. And so here what we see is the material that have two materials of three phases, if you like. So so we have let me explain here. So the dark area everywhere is the soft rubbery material that deform a lot. So this grayish area is stiff inclusions, and these white holes are actually void, so there is no material there. So we can say that it's a heterogeneous material. So there are three phases. So there are voids, there are inclusions, and there is a matrix phase. And so we compress this material here, and you can see that at a certain point these voids collapse, and then they rearrange in different configurations. And so there is some notion of chirality that is happening then, because we have these inclusions here that regulate where the pattern can go after that or cannot. So you break that pattern and you force the material to go elsewhere. So the one thing that you notice here, and that's just, again based on the behavior of material with periodic voids, is that when the voids collapse, so that exerts also the negative Poisson ratio behavior, right? So we compress it in this direction, and the material doesn't expand in the other direction. That is the characteristic of that. And again, so the inclusions, stiff inclusions, provide the means to regulate what patterns you can get. So if the voids, collapse of voids or produces an interesting pattern, but then you cannot access some of others without constraining that in a certain way. So it provides some tunability with this. Okay, so now schematically, that's what happens, is right. So we apply deformation, and then we can monitor or define some measures that one may call Poisson's ratio, but okay, large deformation probably is not entirely appropriate measure, but we can define something that an engineer could connect to. So the measure of the change in the volume, if you like, and then we can actually think so that the instability phenomena is related to the Poisson, to the appearance of the negative Poisson ratio, but this is not necessarily the fact. And now if we look where it happens, so that's the part where we have the regular Poisson ratio, okay, for slightly compressible material, because it's porous material, so it's not 0.5, as for a rubbery material. And then we have this buckling very prominent point when the material start to rearrange. And as you can see that so there is a whole process until we actually get to the negative Poisson ratio or zero Poisson ratio behavior. And that's basically just related to the change on the geometry and not to the instability itself in many ways. So instability is just the means to go towards the geometry that produces negative Poisson ratio behavior. And so here there is, by the arrangement of these figures, you would expect here another one to appear. That has to do something with the elastic wave band gaps, and that's why I moved it to our second part of the talk on acoustic metamaterials. So you will see this picture again when we'll have additional information here on that, but just in a little bit. Now, So let's use a little bit the knowledge that we gained from the laminates, from very simple laminates, and just expanded to very interesting microstructure behavior here. So what we have here is this hexagonal network of stiffer material, right? So that can and embedded here there is a soft matrix in between. And so what now we have two parameters. We have the ratio of the thicknesses of the matrix material and the stiffer layer, and we also have the contrast in the stiffness. And so that basically allows us to choose what, by tuning these parameters geometrically on the material that we use, we can basically tune the critical wavelengths for the that will develop here. And so with this idea, now let's see what we can do. So we can design a situation when we have a wavelength that is we have more wavelengths here in the scenes at one unit cell, and that's the pattern that would be produced out of that. However, we also can go into the situation when we pre-design we choose the materials and the geometry such that we have exactly one wavelength here. And so that's a very nice and beautiful pattern that you obtain by certain instabilities here. So now we can go forward with that and can say, okay, let's design such that the unit cell will be too small for my instability to develop, and I will have only half of the wavelengths here. And that's what you obtain, is an interesting structure here. So you can continue with that even more when, again, the unit cell is not enough to accommodate the wavelengths of the instability, how that net link wants to back out. And that's where this interesting patterns start to emerge, and they may, in a sense, something similar what happens in the biology. However, of course, there are very complicated processes happening there, and it's very remarkable that some similarities here can be seen from consideration of purely elastic mechanical system that hopefully can also provide some insight for formation of patterns in soft biological system. Also, of course, a much more complicated process, and many more parameters need to be accounted for. Now, for going back to the our synthetic materials, so again, similar to laminates, we also can create a map pre-designing these materials. So we can, based on the stiffness ratio or the geometrical parameters, so we can trigger these different functions, different microstructures, and hence different functions. And so finally, with instability, so I'll show you something very interesting that we found working with my students, and as I mentioned, Turkish Dora Pelicity that worked with me back at the Technion on this publication in Advanced Materials. So the system that we choose to illustrate the phenomena is relatively simple. So what you see here, again, so the dark area here is soft rubbery material, and these are basically circle inclusions in 2D. And so this is a plane strain type of deformation. We apply loading in this direction, but you can see that in this situation, the inclusions are packed quite densely, and so they need, also they will need to rearrange somehow, but they will need to find a way to do so. And appears, yeah, so that's what happens. But now to see what actually happened here, probably need some help to draw some lines and arrows. And it appears what happens here is that they collectively rearrange into some sort of subdomains here with certain orientations, and they do not form these classical wavy patterns. And this is happening, okay, so now you can see the difference between these two, just to see that doesn't happen only for this case. so now we change the spacing between these columns of inclusions, and you can see that the similar behavior can also be observed here. So one thing is that it happens where basically the analysis, the theoretical analysis, predict the what is called long wave instabilities and not this microscopic type of instabilities. However, you can see that the clearly what we obtain here is that there is a characteristic wavelength of that instability induced rearrangement, and that is interesting how to capture in the analysis of instabilities that we are using as as we go basically into post-buckling regime here. Now, so just a little bit more information and insight on what happens after that. So one of the things that we can do is to characterize this behavior by measuring this orientation angles of these domains. And of course, in the beginning, this orientation is zero, so there are no domains basically. But then after we apply deformation and the induced instability, that's where this patterns start to grow and that the angles start to evolve. And so very finally, just to illustrate, I mean, at least initiate some thoughts about the understanding of the formation of these patterns, is the simple example of the transition of the from this microscopic to this domain formation patterns. And so the transition is very easily can be illustrated here. So let's say we have this column of isolated column of these inclusions, and then, as I already mentioned, in that case, you can consider this column as effectively a reinforced region of the material. So it will behave stiffer in a way like a laminate. And then if you compress it again, so that also will show you behavior very similar to laminate of this wavy pattern. Now you can start putting them closer, so they, in the hope that these columns will start to interact, or at least to communicate somehow. So they need to buckle together, so need to accommodate each other needs, let's say, and that will indeed happen, but not yet. So they're not close enough to induce differences, so you see that the wavelengths doesn't change much. But then, of course, as we put them even closer, that's where the wavelengths start to change compared to the previous ones, because they already need to account for the behavior of the neighbors and when deform them. Now, at this case, we put them probably already too close, so the material becomes somewhat frustrated, and it actually now needs to find something new because it cannot just simply go to this classical wavy patterns of this. All right, so this is just some illustration or initiation of some thoughts regarding the formation of this pattern. That also actually observed in very different systems of the twinning patterns that are forming in different systems. All right, so now with the remaining time, I hope I will have a few minutes to go for discussion of the some applications that we envision for that, for manipulation of elastic waves by instability. So, and one of the example is again for example for this system is that for certain system, we can induce the band gaps. And I'm not going too much into that, but this is the classical way how you would see these dispersion curves. This is the mapping of certain paths of the Wavenumber in different directions. And there's different branches of the elastic wave propagation. So this is the frequency here, normalized. And you can see that this is for undeformed case, and you can see that for the deformed case, there is a whole region of frequency where elastic waves cannot propagate, and so that's when we apply the deformation, exerting the changes in the In the microstructure material buckled, went to post-buckling, and that's where we open this band gap. So potentially can think about canceling these frequencies, and they cannot, at this frequency range, waves cannot propagate in this material. So this is interesting, but rather complicated mechanism here, so maybe not that easy to see what actually will happen. So I'm going to illustrate this more, but then we'll try to answer the questions: what actually happens and why we induce any changes in the elastic wave propagation in exotic band. So with the promise, there is a lacking image here. So it's also for this negative or auxetic materials, when we have the instabilities, then we enter the negative Poisson ratio behavior. And that's also where we can open additional band gap at low frequency range. So I have to say here that the existence of band gaps here is no surprise, and actually they exist even in the undeformed configuration. So you just need to look at the high frequencies. There will be many of these. But typically, within these structures, if you're looking for the band gaps, what you're interested in to find some at low frequencies, because that would mean that you don't need to have a very large system here to actually go to the low frequencies. So because you always can go to low frequencies by just increasing the size, but if you want to isolate, for example, your room from a noise from outside, you don't want this material to take another 1 meter of that. You want it to be a thin layer, and then for that, of course, the ability to open the band gaps at low frequencies is important. Okay, so now one more example of actually we're already starting to look into what happens when we approach instabilities is so these dispersion curves for the frequencies, again, normalized wave number. This for we kind of started from the more complicated things, and now we're going to simplify it more and more to get to the bottom of things. So this is for laminate. And this is a classical curve how it will be going to laminate. We send a wave along the layers because there was basically no variation in properties in that direction. So there will be no band gap, and we also will have somewhat of that sort of dispersion relationship. But as we apply deformation and compress it more and more, you start to see some interesting behavior here in this omega k dispersion relation. So you see that negative slope here, and as a result, if you look in the group velocity, so you obtain this region of negative group velocity for certain wave numbers. And basically what is interesting is that actually the material is still stable. So geometrically we didn't change much. We didn't exert the buckling there, but when the material is still stable, you near the instability, the material start to feel that at certain wavelengths, with certain wave number, there will be something funny that will be developing. There will be soft modes, and that manifests in appearance of this negative group velocity. Also, some illustration on how the modes of propagation change as we go from undeformed to the compressed material. So still. This illustration wavy mode, so the material, remember, is still a flat layer, just compressed very close to instability, called marginally unstable, and that's where you obtain this negative group velocity. And this is universal, of course, for this one example of the laminate, but this is a universal behavior for any material that is brought close to instability. Now, again, so to illustrate this point, you also have this in 3D fiber composite. Of course, it's a little bit more complicated, but you also have this similar type of behavior when you're going to instability. There are two branches, of course, that we consider shear waves in 3D. And now, all right, so we're going from somewhat exotic materials and laminates, and like what is actually happening here. And probably the good thing to actually to do is to look into completely homogeneous material and see what happens here. And the analysis is, again, it's just like, okay, so this homogeneous material initial state is deformed, and then that's where we mapped into in deformed. So that's where your small amplitude waves propagate. That's where we do the analysis. And so again, this incremental motion that's superimposed well, on the deformed state, so that just to illustrate that. And so to illustrate that, I need to just to go a little bit more back, and the sake of time, need to be even faster. And just to remind you about these two relatively simple material models, Neuquén and Gent material model. Here the difference between them is that so Neuquén is stress-strain relationship between them, so weakly nonlinear, and in Gent we have additional parameter, the so-called locking parameter that allows us to tune this stiffening of the material to obtain more nonlinear behavior. So in that sense, I will be using this to tune the stiffening with deformation as we continue. And so, and so for homogeneous materials, of course, when there are no deformation, and so this polar coordinates of phase velocity and no deformation, so the normalized again, the material is isotropic, and so there is no preference in the direction of propagation. But as you start deforming the material to quite extreme levels, what you will see is that by deformation, you effectively, well, that's what this model predicts, the velocity will increase with the factor of the stretching or compressing, depending on which direction you send your wave relative to the deformation. And it appears that phenomenon you can also use to produce an interesting type of behavior. You can disentangle, you have an interface of this deformed material and undeformed material. Then you can manipulate, you can actually make these elastic waves to disentangle and send the pressure and shear wave in different directions that of course typically travel together. And this is the reason for that pressure waves are not really much affected by the deformation unless the material is quite compressible, which is not always the case for soft materials, while shear waves are actually very sensitive to this deformation, and so they kind of follow what you apply in terms of global deformation of that. This, in fact, I'm not mentioning that very much here, but that also can be tuned by additional fields, not only mechanically, but additionally by, for example, electric or magnetic field. And we have some work on that too, but I will probably not have time for this, and hardly have some time to finish the only mechanical stuff to consider. And now, finally, so after we consider that material, so we know how the deformation changes the wave propagation homogeneous material. Now we want still to couple this with the microstructure, with the geometry. So we have a geometrical effect that changes as we deform, and we also have the material effect that as we deform, the properties effectively change. And a very good example to look into is actually the laminate composite, because what happens in that composite is that unless we apply a compression and make it buckle, but if we just limit ourselves to tension, then we immediately can, a very simple way, we know how the geometry change with the deformation, basically scaling with the stretching ratio, depending on what type of deformation you obtain. And then also the properties of each material we also can express exactly, have exact solution for laminates for large deformation. And so now we have this exact solution, and then based on the exact solution, we can construct the effective energy functions. And here again, you have volume fractions, you have properties, shear modeling of each phase, and then based on that, you can do all the machinery, all the mathematics behind that. You can calculate the acoustic tensor for that, and then you can calculate the eigenvalues of the acoustic tensor, and that will provide you these velocities for the material, so as function of the deformation that you apply. And so that would provide information on homogenized long wave response. But you also, for certain cases, you can write explicit expression. Again, they just back to very early works on that. So there is, for example, can be found in work by Rita. The dispersion relation for laminates can be given, and it basically connecting dispersion relation, basically omega with k in this compact form. And the only thing that we're doing here for the dispersion relation for laminates is that, all right, so there are the few things that we actually need to account as we deform. So the velocity in each material in the phase A, phase B, matrix and fibers can change with deformation. And there are also very relatively simple behavior changes in geometry, in the actual the thicknesses of the material of matrix and fiber that change with lambda. And if the material is compressible, well, even slightly, we also can account that. So the density can be changed with that. And so, and then that's how this dispersion relation will look like. This for shear wave, and this is for pressure wave, and these are regions for the band gap. So there's nothing really very new about that. Okay, so we apply the deformation here. Now, so one of the comments here is that we can use that to actually optimize and maximize this volume, these band gaps. So, for example, I'm taking the low band gap for different contrast and stiffness composites, and then you can find a particular situation when we, instead of something very tiny and almost negligible band gap, you can maximize and obtain very large band gap if you choose the configuration of your material more, and then you can tune it even more with deformation. There's a tunability here is looking like that. Okay, so these are your band gaps, and for different volume fractions you can create this map. So there is a shear band gap and pressure band gap, and okay, so we can also define what is a complete band gap, but we don't want to look into what actually propagates there, but just saying that we want in a situation when another pressure shear wave will propagate. And now, if I apply the deformation, so what you see is that you have a shear band gap that actually, so that was undeformed lambda equal 1, and so this 50% of deformation. So you see that shear band gaps, for whatever reason, and we'll need to get to that, stay the same, and the pressure band gap moved up. And so, of course, complete band gaps, these dark areas, are changing in a complicated manner. But in a way, this is a very simple thing that obtained here, that we obtain. And so now to illustrate it even more, so I put these band gaps as a function of the stretch, and you can see that for the Neoken material, that's actually exactly what happens. So shear band gap just stay and don't really change much, and your pressure band gap change quite a lot. So, however, you can see that for gent material, for that one, that is shows much more linearity, more stiffening effect, for us to say. So you see that you have this tunability, and we'll get to that again. And so this is for 2D deformation. Now, just to illustrate that this is not limited to this in-plane deformation. So the same similar behaviors also for equibiaxial deformation. So it's already a 3D type of deformation, and then also for Neoken material, the shear band gaps stay the same, and for gent material they start to change. And the reason for that is basically, again, just to summarize this very quickly, is that while for pressure band gaps, the changes are mainly through geometry change, basically thickness change in the laminate. But for shear band gaps, that can be seen in the dispersion relationship very clearly. There is a competition between the changes in the geometry when we apply deformation and the material properties. And it just appears by some sort of magic that the dependence, the material dependence on deformation and the geometrical dependence from near-Euclidean material cancel each other entirely. Exactly, that's why we see that there is no sensibility for deformation in near-Euclidean laminates. However, we can use some other material that show more of the stiffening effect and more nonlinear behavior, and then you basically can tune, it can increase the contribution, the role of the stiffening of the material, and start winning over the geometrical effect of the changing thicknesses in this. So these are just some illustrations of initial thoughts on how the deformation, changes in geometry, and material properties play a role into the formation of band gaps and unusual wave propagation behavior for materials that experience instabilities. And I probably will stop here with just some reminder of the first part, and I'd like to thank the organizers again and my students that helped me to explain, or at least to find some of these interesting behaviors. Thank you.
Thanks, Stefan, for this interesting talk. So audience, we are open for questions. You may please type your questions in Q&A box.
Apologies that I have taken probably more time than I planned. I had to go faster on certain parts, especially towards the end. Happens to me quite frequently.
Anshul, can I ask a question?
Yes, sir.
Yeah, Stefan, nice, very nice talk. How sensitive are these patterns to randomness in the microstructure? I mean, is it possible for the long wavelength patterns to degenerate into short wavelength ones, or vice versa, because of randomness?
Thank you. That's very good question. And so some of these patterns less sensitive than the others. Like, for example, these ones with collapsing voids, they are almost they would ignore any imperfections until they become really very large. But for other systems, it is true that need to be very careful with what you give as an input and with these imperfections. And it is possible that if the imperfection was too large, then it can actually trigger the material to do something different. But there is a way to check that. So you can monitor energies. You can basically do all the analysis by changing the initial imperfections and their amplitudes, and they see where you start to exert different patterns because of that. Because you don't want to induce artificially something that system doesn't want to develop. So we use different types of disturbances there, including some random ones, to get to the bottom of the things.
I had another question. How difficult is the inverse problem? So given a desired band gap, can I design a microstructure? Is that a possibility, or it's too remote?
Well, there are actually some works, and especially nowadays when the AI, machine learning things become very popular. So there are quite many recent works on that. You can use brutal force, just changing parametrically the microstructure and gaining the insights how they change the band gaps. But yeah, so it is possible. And if you want to pre-design not just the situation with the band gap, but the whole transmittance spectra for that, that will be already more challenging, then that's where you have lots of data, and that's where machine learning can say you, okay, take this one microstructure that will give you the desired transmitted spectra and attenuation.
Okay, thank you.
Yeah, thank you.
Yeah, there is another question from Madhav.
Yeah, can you hear me?
Yes.
Okay. So my question is regarding the domain pattern, the domain formation in the soft particulate composites. So are these patterns caused by a linear instability, or is it a secondary instability, that is analysis about a weakly unstable steady state?
Yes, so the instability analysis is linear, superimposed on large deformation. But then after that, we do perform the post-bifurcation analysis and make sure, so we actually check if the material is stable after that or unstable and rearranges into new pattern. It appears that material is stable during the post-bifurcation process as it gives rise to this pattern formation. At least we didn't detect anything that indicates secondary instabilities. In some systems, it happens that you have actually secondary instabilities. For example, for that one, for this hexagonal network composites, we detected some of these. But for this domain, let's call it, domain of twinning patterns, so that when material becomes unstable, initially some form that would remind more of a wavy pattern start to form, but then it evolves into these domain patterns without becoming unstable again.
Okay, thank you.
Thank you.
Okay. There is one more question. What is the range of your input frequency? Are they in megahertz?
Well, this is it's a good question, but basically, this is a normalized frequency that is related to the size of the microstructure. And that can be anything, especially in simulations, until you do experiments. So it can be anything, right? So just at certain point, you need to say if the microstructure is micrometer size, then you go to a higher frequency, or is it of millimeter size, and then you go to low frequency, just this,
Yeah, there is another question from Sudeep. You can ask the question.
Yeah. Hello. It was a nice presentation. I just wondering one question, that how the scale parameters are chosen, particularly for the auxetic metamaterials. When you analyze the auxetic materials, if suppose you are framing it from one scale to the another scale, particularly the hexagonal structure you have shown. So my question is, how the scale have you chosen? You must have chosen the scale parameter, right? Hello.
Oh, yes, thank you. So for this hexagonal network composites, right? So that I have here on the basically. So we start from simple composite hexagonal network, but then we think that we basically rely on what we learn from laminates. So we can predict the wavelengths or estimate the wavelengths based on the parameters similar to what we seen in laminates. Again, and what drives these wavelengths here is your choice of the thickness ratio between the matrix here and stiffer layer, and also the contrast and their properties. So because these two parameters define what will be the wavelengths here, and therefore then you choose the right thickness, or right, depending on what you want, and then you can observe this close to what you expected, these wavelengths here, and basically that's the whole idea behind it. so again, the wavelengths here is pre-designed through our choice of the material properties of these two matrix and fibers and the thickness ratio. So that's pre-designed.
Okay.
I mean, in conjunction to your this, I mean, suppose if we consider the randomness that, like Professor Vasu also was talking about that, because you have considered the wave, right? So you have defined the equation of the wave, right? But when we are considering the randomness into it, randomness is just like we cannot frame it by means of any equation. Random means it's totally random. So
yeah, I don't want to confuse it with that. So it is correct that the machinery of the instability analysis that I'm using is actually built on periodicity, and I probably misinterpret what the question about the randomness, rather looking into post-buckling analysis when I can add the imperfections in whatever shape and form as a random ones and see how that manifests in the actual post-buckling behavior. So, but most of I've shown is based on the periodic structures, and there was some aspect of random distribution in the fiber composites for which we obtained effective behavior, but there were no real consideration of the wavelengths there. So it was a kind of effective behavior that you can obtain and can estimate when that will become unstable. So that's actually a very interesting direction to explore, to when the material not periodic anymore, but they still may have some structure, or how that randomness that play a role into that. So I have some thoughts about it and some ideas, but not ready to comment that with any level of confidence. So
okay, thank you.
Thank you.
Okay. So there are no more questions. So thank you, Stephen.
Thank you. Thank you very much.
Yeah. So I will finish the session now. Thank you very much for this talk.
Yeah. Thank you. Stay well and healthy.
Yeah.